I've seen a lot of people spend 4, 5, even 6 minutes on this question, but I'm not convinced that we need pen and paper here. In fact, I think that with the right approach to data sufficiency and with some good visualization, we should be able to solve this question in under a minute without putting pen to paper at all. So let's see what that would look like right after the intro. So starting with statement 1, we are told that 2 of the measurements are exactly 5, but we don't know anything about the third one. It might also be 5, it might not be. So visualizing this in my head, what I'm imagining is extremes, different extremes for that third measurement that we don't know about. That third measurement could be close to 0, call it 0.0001, in which case we have essentially a square that has an infinitesimally small width. It's basically a 5 by 5 square, essentially. It doesn't really have any depth at all. So the volume then would be basically 0, very close to 0. But the surface area would be, I think it's 50 approximately, right? Because you'd have a 5 by 5 on either side of that square. And so the surface area would be about 50 and the volume would be basically 0. So volume over area would be 0. In the other extreme, you have 5 by 5 by a million. And if that's the scenario, then the volume would be 25 million. And the surface area would be, I don't know, somewhere around 10 million. And the ratio that the question is asking about, in this case, wouldn't be 0. It would actually be quite large. So I can see, without putting pen to paper, just by kind of visualizing and thinking about extremes, I can see that statement 1 is not sufficient on its own, because you're going to get very different ratios of volume to surface area depending on what that third measurement is. So doing something similar for statement 2 on its own, what do we know from statement 2? We know that it's a cube. Right? This rectangular solid is no longer a rectangular solid. Well, I guess it's a kind of rectangular solid. It's specifically a cube. So what do we know about the ratio of volume to surface area in a cube? Well, kind of similar to what we saw for statement 1, the ratio of volume to surface area is going to depend on the general size of the cube. I mean, if this cube is 1 by 1 by 1, you'd have a volume of 1, but a surface area of 6. So that's a ratio of 1/6, a very small ratio. On the other hand, if the cube is 1000 by 1000 by 1000, then your volume is 1 billion, right? 1000 cubed. But your surface area would only be, 6 million. So 1 billion divided by 6 million is a massive ratio, much bigger than 1, whereas when the cube was 1 by 1 by 1, we got a tiny ratio of 1/6. So that's my way of kind of proving to myself that statement 2 is not sufficient on its own either. Now, when we combine the statements, we can actually tell that it's a 5 by 5 by 5 cube. And since we know everything there is to know about this cube, we could of course find anything you wanted to find, including the ratio of the volume to the surface area. We wouldn't do this at the actual test center, but just for our purposes, let's go ahead with the math. It would be 5 cubed divided by 6 times 5 squared. You can reduce 5 squared from the top and the bottom, and you end up with a ratio of 5/6. If you found this video useful, go to quantreasoning.com for a lot more where that came from. You should also click that like button and let me know in the comments below what you'd like me to make future videos about. And of course, if you haven't yet subscribed, go ahead and do that and click that bell below so you get notified about future videos. See you next time.